Hello everybody, I am Jabin Bano M. Nadaf, Selection Grade Lecturer in Electrical and Electronics Engineering, Government Polytechnic, Belgavi. We are studying Unit 2, Transistors and MOSFETs, and this Unit 2 we have already discussed about the BJTs and the concepts, some of the concept of the MOSFETs, and today's session is based on the characteristics of the MOSFETs. Characteristics of the MOSFETs. So before that, let's have a quick recap of the previous class. In the previous session, we have discussed on the working principle and construction of the N-type enhancement mode of MOSFET. So let's have a small animated video here. So the MOSFETs are the metal oxide semiconductors field effect transistors, which usually have 4 terminals: drain, gate, source and substrate. The work of the MOSFET is they are used as a switch and as well as amplifier. In MOSFETs, basically the operation is unipolar, that is any one type of charge carriers help for the flow of the current. Based on unipolarity, we have the N-channel MOSFET and P-channel MOSFET. In the P-channel MOSFET, the current flows due to the holes, and in the N-channel MOSFET, the current flows due to the electrons. So we will study the structure of N-type enhancement mode of MOSFET. It has a P-type of substrate into which two heavily doped N plus regions are diffused, and the white one is a silicon dioxide layer which is deposited, and over that we have a metallic layer. So N plus regions, that is blue ones, form the drain and the source terminals, and the gray layer is called as a metallic layer. It forms the gate terminal. If a voltage of VGS is applied between the gate and the source, the holes are repelled by the positive terminal of the gate, and electrons in the p-type are attracted by the gate. Hence they form the channel. Once the channel is formed, if a voltage of VDS is connected between the drain and the source, the current starts to flow from the drain to source. In the video, there is a movement of the electron from the source to drain. So we saw that in the animated video, the channel was forming. Once the channel was forming, the value of VGS was less than VTH. The channel was not at all forming, and in this case the drain current was 0. So once the channel is formed, the value of VGS was greater than VTH. So with this much concept, let's move on towards the today's topic, that is the MOSFET characteristics. So what are characteristics? Characteristics tell us about the performance or behavior of the device, like how the living organisms or every living organisms have a unique characteristics. Similarly, each and every electronic component or any machinery components, they also have their characteristics based on which they are suited for a particular type of applications. So the N-channel enhancement MOSFET, it has two characteristics. The first one is output characteristics. Second one is transfer characteristics. The output characteristics called as drain to source characteristics, transfer characteristics called as gate characteristics. So already we have discussed this drain to source characteristics called as the output characteristics, gate characteristics called as transfer characteristics. So to obtain any characteristics, we need to have the experimental setup. Experiment setup to obtain the VI characteristics of the MOSFET. So what are the characteristics we are obtaining? We have to obtain the output. We have to obtain the output characteristics as well as the transfer characteristics. So we have a MOS here, three-terminal device, drain terminal, gate terminal and a source terminal. So the drain terminal, if you look at, it is connected to the positive of the VDD, and the source terminal it is connected to negative of the VDD. It means that a varying voltage of VDD is connected between the drain and the source terminal. So the output current is ID, output voltage is VDS. Therefore, the output parameters are ID and VDS. ID and VDS. If you look at the gate terminal, between the gate terminal and the source terminal, I have a voltage source VG, which helps me in controlling the value of the VGS. So what is VGS? It is the input to the MOSFET. So the input parameter is VG. So there are three parameters which decide what characteristics we are obtaining. If we want to know the behavior of the output parameters, it is called as the output characteristics. If I want to know the behavior, if I apply input voltage, what is my change in the output current, or how much how much input is transferred to the output, then they are called as transfer characteristics. If I want to know only the output data, then they are called as output characteristics. To know this is ID, VDS, VG, what they are. ID we know it is drain current, VDS it is the output voltage across the MOSFET, and VGS it is VGS. VGS it is the input voltage to the MOSFET. So ID it is the drain current, and so we will to read this drain current we will connect a millimeter so that we will read the value of ID. Then VDS it is the output voltage source. To read this one we will connect a voltage source or a digital multimeter. To read the VGS we will connect the voltmeter. So we require two voltmeters or two digital multimeters to read the value of VGS and VDS, and a ammeter to read the value of ID. So this is a basic requirements. So if we are varying VG or we are varying VDD, whether we are changing VDS or whether we are changing ID or I am changing VGS, depends on what type of characteristics we are obtaining. Whether we are obtaining the output characteristics or whether we are obtaining the transfer characteristics. So what is the output characteristics? It is defined as a plot of the output current. What is the output current? ID versus output voltage. What is output voltage? VDS or drain to source voltage. When for fixed or constant values of VGS. So written in the form of the statement ID versus VDS for constant values of VGS. What is the meaning of this? Fixed or constant values of VGS. Let us go back for the experimental setup. So here see, here. So let all the power supplies be 0. Let VDD be 0 and let VG be 0. So we are obtaining what? We are obtaining the output characteristics. Means ID I have to plot on the graph, I on the y-axis, B on the x-axis. ID because we are talking of the output characteristics now. The output current is ID. VDS because we are talking of the output voltage now. So if I plot ID versus VGS, then I am going to get the output characteristics. So if I vary ID and variation should be there in the VDS, or if I vary VDS, change should be there in the ID. Okay. So to obtain these characteristics, I have to vary the VDD. Suppose for example, I will vary VDD now. So VDD varies, ID starts flowing. But if the MOSFET itself is off, then how much ever if I vary the VDD, VDS is going to change. But ID is not at all flowing because the MOSFET is off. We have to ensure that I will vary VG such that VGS means the gate source voltage, input voltage of the MOSFET is just equal to VTH. If this is equal to VTH, then the MOSFET is on. So let for example, we will assume, in our example, I will assume VTH is equal to 2 volts. So if I vary the power supply of this such that VGS will be equal to 2 volts, then immediately this MOSFET is on. So then if I vary VDD, according to the VDD, VDS and ID will change. So according to the VDD, VDS and ID will change. I will look at the emitter and voltmeter to obtain the VD and ID readings. This I obtained for one value of VGS. What is the value of VGS? It is now VTH. So I will call this VTH as X1 volts. So again, now I will recall my definition of the output characteristics, that it is a plot of ID versus VDS for fixed values of VGS. So I will go on taking reading 1, reading 2, so on I will complete my experiment. Then afterwards I will reduce the power supply of VDD back to 0, again increase VG. So VG, now I will make it as 3 volts. If VG is 3 volts, it means my VGS is 3 volts. This 3 volts, VGS is 3 volts. So this 3 volts I will call it as X2. So I will write for VGS, say for example equal to X2. X2 in our example is now what? X2 for in our example is now 3 volts. Earlier we took VGS as 2 volts. For this value of VGS, I varied the VDD such that change in the VDS or readings of the VDS and ID are obtained. Now what I did, after taking this full readings, I reduced the VDD back to 0. VDD means this power supply it is. After that, what I did, I shifted to the input side. Now here I changed the value of VGD to new value. What is the new value? That is the 3 volts. So after that, I will fix to 3 volts, come again at the output side. Again, I will vary VDD and take the readings for output voltage VDS and output current ID. This is the meaning of the output characteristics. It is a plot of output current ID versus output voltage VDS for fixed or constant values of VGS. This is the meaning of the output statement what we have discussed. So let us come back. So about the output characteristics. So these are the characteristics what we are obtaining from the output characteristics or taking the readings of ID and VDS. So taking these two set of readings, this set of reading and this set of reading, I am able to get the output characteristics. So this is the output characteristics what is seen on your screen. So we studied that the output characteristics is a plot of ID versus VDS for constant values of VGS. It means for VGS say equal to X1, for VGS say is equal to X2, I am getting the set of readings, ID reading, VDS reading. After completing this, I will come to the second step. I will set the value of VGS is equal to X2. I will again take ID reading and VDS reading. So this is called set of characteristics. Set of characteristics. So I will just plot the characteristics. So this plot of ID. Usually the drain current is in milliamperes. VDS. Okay. So if the value of VGS, as remember the experimental setup. If the value of VGS is less than VTH, we know that the MOSFET is off because the channel is not at all formed. In this case, the drain current will be equal to 0 and your MOS will be off. So this is called as the off state. So what is the voltage at which the MOS will be off? The value of the voltage is less than the threshold voltage. Once the value of the VGS becomes equal to VTH, the channel is formed. Immediately a very small amount of drain current starts to flow. So this will be depicted in this way. This is the output characteristics for VGS is equal to VTH. Why it is the nature we will discuss now. Why it is in this way. Okay. So below the value of, if the value of VGS is below the VTH, means this part, below VTH means it is a MOSFET is off because no channel is formed that time. Okay, but if my value of VGS, what is this VGS? VGS is the input voltage connected between the gate and the source. If the value of VGS is greater than or equal to VTH or only greater than VTH, then the channel is formed and the drain current now starts flowing. If the drain current starts to flow, then what is the nature of the drain current? It is flowing now. So what is the nature of the drain current? So since in the channel there is a deposition of more number of electrons, the drain current increases linearly with increasing the output voltage VDC. It means that as I vary the VDD, the VDS increases. So increase in the VDS will increase the ID. How? Linearly. What is meaning of this word linearly? Linearly means it is what? It is a, just show you here. So if the IV graph or the VI graph or any component is a straight line, it is called as a linear. So if my value of VGS becomes greater than VTH, that is the channel is already in the conducting state, just started to conduct. That time if I vary the value of VDS, ID will increase linearly. Means what? So here I will get a linearity. So this I will get a straight line. Just it is a straight line in this section, just for you to make you understand. It is just not correct. I will redraw it. So it will vary linearly. Just I will draw. So we studied that when the value of VGS is equal to VTH, ID will vary linearly. So in this part, varying linearly, it happens because in the channel we have accumulation of more number of the charge carriers. Now I again increase VDS. If I again increase VDS, then at the input side my VGS will be much higher than the VTH. This is a condition. So the drain current, what? It increases linearly till certain point only it is increasing. Beyond a certain point, as I increase the VDS, the drain current is not at all increasing linearly. Instead, the drain current is remaining constant. So this part is called as the constant. Why it is constant? See, there is increase in the value of the VDS. So VDS is the x-axis. It may increase from 1 volts, then to 2 volts, then to 3 volts. So 1 volts, 2 volts. I'll vary the VDS to 3 volts. Then I'll vary the VDS to 4 volts, etc. Till say 1.5 volts or something, the drain current was increasing linearly. But after this 1.5 or something, how much ever I increase the value of VDS, the drain current is approximately remaining constant. So this set of characteristics I will just obtain for a little bit higher values of VGS, say x1 volts. The same thing I will obtain for VGS is equal to VTH, but in this condition the drain current is very small, therefore we can't predict the characteristics. Therefore I explain the same for you with a higher value of VGS. So I have increased the value of VGS. Next, again if I increase the value of VGS, then again the drain current will repeat. The same characteristics is repeating. The same characteristics is repeating here. Again, if I increase the value of VGS, again I will get this characteristics VGS. So from this characteristics, what we are going to study? So we are going to depict or study that it, it will exhibit different operating regions of the transistor or the MOS devices. Let us come back for our slides. So this whatever just we discussed now. So see here, if the value of VGS is equal to VTH or below this, the drain current will be 0. So approximately 0. So here the current is very negligible. So in this below the value of value of VTH, that means if my VGS, if it is less than VTH, so it is below the value of VGS equal to VTH. That time the MOS is off. The MOS is off. It means that the drain current is 0. So this region of operation, it is the cutoff region. So what is the cutoff region of the MOS FET? So if my value of VGS is less than VTH, no channel is formed. That means the MOS is off. It means the drain current is 0. So it is called as the cutoff region. So here you can obtain the cutoff region of the MOS FET. So once my value of VGS becomes greater than or equal to VTH, I know that the MOS is on. So in this, how is my variation of ID? The variation of ID can be two methods. One is ID may be linearly varying with VDS. It means an increase in VDS, ID increases linearly. I will explain for this set, second set only. So ID increases linearly till it reaches a certain voltage. What is this voltage? It is called as VP, pinch of voltage. Pinch of voltage is what? It is the voltage at which the drain current stops increasing linearly. That is called as the VD. That is called as the pinch of voltage. So at a point of VGS is equal to, at a point of VDS is equal to VP. So this voltage is the value of VDS where it has reached the VP. So after that the drain current is remaining constant. So after the value of VDS equal to VP, the drain current is becoming constant. Okay. Similar set is obtained if I increase the value of VGS from x1 volts to x2 volts. So this is the characteristics. Similarly for this one. Similarly for this one. Okay. So now the MOS on. So we have two phenomena of the drain current. So in the linear part, that is called as the ohmic region or the linear region of the MOS transistor. If the drain current is constant, that is called as the saturation region of the MOS FET. So based on the application required, my MOS FET can operate in the saturation region and cutoff directly. It can shift from cutoff to saturation, saturation back to cutoff, or it can operate only in the linear region. So again we will just read this one. The output characteristics, they depict the MOS FET has three different regions of operation: the cutoff region, linear region or ohmic region, and the saturation region. So we know that in the cutoff region, the MOS FET is off, and this occurs at VGS is less than or equal to VTH and ID is 0. In the linear region, the MOS FET is just on because the value of VGS is greater than or equal to VTH. Here, as VDS increases, the drain current increases linearly till what a voltage called VP, it is called as the pinch of voltage. Afterwards, the MOS just behaves like a simple resistor. So the MOSFET in the linear region behaves like a simple resistor. So what is the pinch off voltage? It is the voltage at which the drain current stops increasing linearly, or the drain current is becoming constant. So if my value of VGS is much greater than VTH, or after the pinch off point, the VDS is greater than or equal to VP or equal to VP, the drain current becomes constant how much ever you vary the value of VDS. So from the output parameters, what we are going to extract? We are going to obtain the drain resistance and the gain or amplification factor of the device. So from the we obtain two parameters, drain resistance RD and gain of the transistor. What is the drain resistance? Resistance, we know that it is V divided by I. So we are talking of the output resistance, therefore output voltage is VDS, output current means it is IT. So change in the output voltage to the change in the output current. So RD is given as the ratio of change in the output voltage to the change in the output current. As RD is equal to delta VDS divided by delta ID. Usually it is measured in ohms. So if we look at the output characteristics, so I will draw only one set of characteristics only for one value of VGS. It is output characteristics only, but only for one value of VGS I am drawing. So in the linear part, if you see, it behaves like a simple resistor. Just we will find out what is the value of RD here. So I will take 2 points. One is here, say X. So A I will write, and there is here, I will write it as B. I will drop this A point on the y-axis. I will get 2 points of the current. This is known as delta ID. If I drop A and B points on the x-axis, again I will get 2 points here. This is called as delta VDS. So from the graph, directly I can extract the output or the drain resistance. So what is the gain? The gain is the amplification factor. By how much your output is increased with respect to the input signal. That is called as the amplification factor. So it is nothing but the output voltage or change in the output voltage multiplied by GM. So what is this GM? The GM is a parameter. It is called as transconductance, and usually we obtain this from the transfer characteristics. So let's move on to the next characteristics. The transfer characteristics or the gate characteristics. It is a plot of output current, or drain to source current is the output current ID versus input voltage for fixed value of VDS. So I can write ID output current versus input voltage. Input voltage is VDS. If you look at the experimental setup, see, your input voltage is VGS, your output is ID. So ID versus VGS for constant values of VDS. Let us come back to the board. So just what are the transfer characteristics? It's a plot of output current versus input voltage for constant values of output voltage. So, input side the power supply is VG, which helps in the changing in the VGS. Recall the experimental setup. At the output side the power supply was VDD, which was changing the value of both VDS and ID. Now what I will do, I will fix my value of all the power supplies. I will set to 0. I will fix my value of VDS. Say for example it is X1. Then I will vary. How I will fix the value of VDS? By varying the VDD, output side power supply. I will fix this VDS by varying this one. I will keep quiet, shift at the input side. Then I will vary VGS such that I will get the ID readings. So I can tell that the transfer characteristics is a plot of ID versus VGS for fixed values of VDS. Again I will increase the value of VDS to a new voltage x2 volts. Again I will vary the value of VGS. I will get the value of the drain current. Like the set of characteristics, different sets of characteristics can be obtained for different parameters. So in the earlier class, start of the class, we discussed that your VGS, VDS and ID, all they are controlling parameters. The VGS entirely controls the VDS and the ID. Therefore, let us draw the graph. All the graphs are IV characteristics only here. Output current ID, usually it will be in milliamperes. So input voltage VGS, it will be in volts. So when the value of VGS less than VTH, the MOS is off. So at this, the MOS is off. Afterwards, the MOS is on. So this is called as one set of characteristics. Say for VDS is equal to X1 volts. We are getting this. And now I will increase the value of VDS. I will get this type of curve. VDS is equal to X2 volts. Again if I increase, I will get this one. VDS is equal to X3 volts. So if I increase the value of, if you look at the graph, if I am go on increasing the value of VDS, the VGS is decreasing. It means that the VTH also decreases. Means if I increase the value of D to S volts, the threshold voltage of the MOS reduces. This parameter you can obtain from the transfer characteristics. Then what data you can extract? GM, nothing but the transconductance. This you can obtain from the transfer characteristics. So what is GM? It is the conductance. It is I divided by V. Capital I divided by capital V. It is a plot of output current. Therefore, it is ID. Input voltage. It is VGS. So I can call GM as change in the output current, change in the input voltage for constant values of VDS. Once I get the GM, then I will get the gain which is multiplied of Gm and the VDS or delta VDS. So let us go back for our slide. So this is the transfer characteristics. So we already discussed this. So until VGS is equal to VTH, the MOSFET will be off, then it will be on. Here two conditions we are getting. Okay. So again, if I increase the value of VGS, then ID is going to increase. So this I obtain for one value of VDS, for a particular value of VDS is equal to X1. If I increase the value of VDS to a new value, then your VGS is going to reduce. So from this lecture, what we have learned? We have learned about the behavioral pattern of the MOSFET. Behavioral pattern means the characteristics itself. So depending on the characteristics, say if I obtain what? I obtain like this, different sets of the output characteristics. Then I obtain what? I obtain different sets of the input characteristics. So depending my application, if my device is such that the drain current is 10 milliamperes, maximum is 10 milliamperes, beyond that it is not operating. Then depending on the characteristics, maximum 10 milliamperes, maximum drain current is 10 milliamperes. This is for which MOSFET? That I will find out by reading the data sheet. Data sheet is a information which gives all the details of a particular MOSFET, such that for depending on my application I can choose the MOSFET wisely. So let's have a quick mind map. So today's topic was what? Today's topic was the characteristics of the MOSFET. So we discussed about the characteristics of N-type enhancement mode of MOSFET in this transfer characteristics and the output characteristics. In the transfer characteristics, we know that is ID versus VDS, ID versus VGS for constant values of VDS. So output current, input voltage. So when the value of VGS is less than VTH, ID is 0. When the value of VGS is much more greater than VTH, ID increases. Earlier it increases linearly. Next ID is constant. So what I can obtain from the transfer characteristics? GM, transconductance. So in the output characteristics, it is ID versus VDS for constant values of VGS. So here we can learn cutoff region, linear region and saturation region. When the drain current is 0, it is cutoff. When the drain current increases linearly, it is linear. When the drain current is constant, it is saturation. What you can obtain here? Drain resistance and the gain of the MOSFET. So these are the references what I have visited: www.electricalforyou.com, electronicshub.org and tutorialspoint.com. You also can visit them for your more information, and the textbooks I use to prepare this content is Electronic Principles by Albert Paul Malvino and David J. Bates, Principles of Electronics by V. K. Mehta, and Electrical Technology Volume 4 by B. L. Thereja. Let's move on for the questionnaire. So the first question for you all is, a plot of ID versus VGS is what? Input characteristics, option A. Option B, output characteristics. Option C, transfer characteristics. And option D, both A and B. So take a 2 seconds to 3 seconds time and think, what is ID versus VGS? ID versus VGS. What characteristics it is? Answer C, it is the transfer characteristics. Next question. From the transfer characteristics, what we are obtaining? Transconductance, resistance, gain, amplification. So from the transfer characteristics, we usually obtain the GM. What is the GM? It is the transconductors. Therefore, your answer is option A. MOSFET can work as amplifiers in which region? Cutoff, linear, saturation, all of them. So think wisely. What is the answer? It is the linear region. In the transfer characteristics, if the VGS increases, what increases? It is ID increases. In the cutoff region, what will be the drain current? See, it is 0. So option is C. So these are the persons who have effectively helped us to create the successful content on the analog electronics. Thank you, one and all.